These are our notes on the definite integral. So we're just going to recap what we've been talking about with the area problem that we've already discussed. So for right endpoint rectangles, if you want to find an estimate for the area under the curve using right endpoint rectangles, the way that we do that is we say that the area is approximately equal to the sum from I equals 1 to n on f of x sub I times delta x, where delta x is going to represent the width of each rectangle. F of x sub I is the height of each rectangle. In this case, those heights are based on the right side of the subinterval. And then we add all of those areas of those rectangles up together to get an estimate of the area overall. For left endpoint rectangles, you get something similar, except that now we've got the sum from I equals 1 to n on f of x sub I minus 1 times delta x. Delta x is still the height of the rectangle, but now delta x is still the width of the rectangle. The height of the rectangle this time, though, is based on the left side of the subinterval. So that's the difference between the left endpoint rectangles and the right endpoint rectangles. And then similarly, we can do midpoint rectangles, where delta x is still our width. Our height, however, is now based on the x value that is exactly halfway in between the two endpoints of the subinterval. So in other words, to find x sub I bar, you average the endpoints of the subinterval. You then input that average into the function, and that gives you the height of your rectangle. So we've already talked about all of these. We do call these Riemann sums, and they are all estimates of the area under the curve. So if we're estimating area, clearly, as we have already shown in our previous discussion, if you estimate area under a curve using, let's say, left endpoint rectangles versus right endpoint rectangles, you get two different answers. Typically, one's going to be a little too high, one's going to be a little too low, depending on whether your function is increasing or decreasing. But the moral of the story is left endpoint estimates and right endpoint estimates are not supposed to be the same. However, if we are calculating the exact area under the curve by using infinitely many rectangles, so instead of using 10 or 100 or 1,000,000 rectangles, we use infinitely many. If it's exact, there is exactly one area under that curve. It doesn't matter whether you're going to use left endpoints or right endpoints, assuming that you are then going to use infinitely many rectangles. So in mathematical notation, the way that we write that is that we say if, when you're doing your right endpoint rectangles, which would be what we see here in this first bullet, using right endpoint rectangles, if we take infinitely many rectangles, we let n, which is the number of rectangles, approach infinity, or we can say that the area is exactly equal to the limit as n approaches infinity on L sub n, which is your estimate of the area under the curve using left endpoint rectangles. Or instead of saying, oh, well, the area, you have to use right endpoints and then use the limit to get the exact area, or you have to use left endpoint rectangles and use that to get the area. Instead, we're just going to say, you know what? We want to leave space for the fact that we can use any type of rectangle. One where the height is based on the left side of the subinterval, the right side of the subinterval, the midpoint. It can be any of them. So instead what we say is that the area is equal to the limit as n approaches infinity. We have this new notation for the height. We're going to use this notation that says f of x sub 1 star. That is still the height of our rectangle. Notice we still have delta x as the width of the rectangle. What we mean by x sub 1 star is that is any value in between, any x value in between x sub 0 and x sub 1. It could be exactly equal to x sub 0, in which case it would be over on the left side. It could be exactly equal to x sub 1, in which case it's on the right side. But it can be anything in between as well. For the next one, notice we'd have f of x sub 2 star. In general, we're going to call those x sub I stars. Okay? We give this a name. We call that a sample point. So it can be the right endpoint value, a left endpoint value, any of them at all. So this is the notation that we're going to start using if we want to start having a conversation about the exact area under the curve instead of just an estimate or an approximation. So before we have that conversation about the exact area under the curve, I want to remind you of a conversation that we had more towards the beginning of the course about derivatives. Okay? If you remember, when we first learned about derivatives, we didn't actually use that word. What we talked about was, first we talked about average rates of change, like slope between 2 points, or average speed, or average velocity. And then we had a conversation about what that was in comparison to instantaneous rate of change. So for example, with the slopes, we looked at the slope between 2 points compared to the slope at one specific point on a curve. Instead of average velocity over a time period, we talked about instantaneous velocity at a specific time. And what ended up happening was, because this idea of instantaneous rate of change had so many applications. I mean, we've done particle problems, we've done optimization, we've done related rates. Instead of having to repeatedly say instantaneous rate of change, we used a different word. And that's where we come up with the word derivative to describe the general idea of an instantaneous rate of change. So the same thing is true about what we just did with area. We took a specific approach to finding an estimate for the area, right? We didn't know how to do it, so we divided it up into rectangles. We used infinitely many of those rectangles and we added them all together. But it turns out that this idea of breaking something down into small recognizable pieces, in our case this was areas of rectangles, and then adding them together, it's not a single solitary idea. When you take infinitely many of these small pieces and add them together, it turns out that that is helpful in a lot of real-world situations. So because we are going to be doing that multiple times, and this is true through Calculus 1 and on into Calculus 2, we're going to take this concept of breaking something down into recognizable pieces, adding those together and taking infinitely many of them. We're going to do this a lot, so we're going to give it a name. What name we're going to use is called a definite integral. So let's talk about its formal definition. The definition of the definite integral. This first paragraph is very mathy in notation, but it is everything that we have already talked about when doing approximations of area under a curve. So first of all, you have to have a continuous function defined for a less than or equal to x less than or equal to b. We take that interval from a to b and we divide it into n subintervals of equal width. That should start to sound familiar. That's what we've been doing when we're estimating areas under the curve, right? We had a, we had b, we broke it down into a certain number of rectangles in our case. The width of each rectangle, the way we found it, delta x, was we took the length of the interval, and in this case, the way we mathematically write length of interval is b minus a. That tells you how long it is. And then we divide it up into n rectangles. Now the difference between what we've already talked about and what we're going to talk about is that in estimating areas, we told you how many rectangles to use. We said use 5, use 10. The deal is, eventually for these, we need to take infinitely many rectangles. And you can't really let n equal infinity. It doesn't work like that. But what you can do is let n approach infinity. So we're going to need to leave this as a general n for these. We're going to let x sub 1, x sub 2 through x sub n be the endpoints of these subintervals. And then here comes that new notation. x sub 1 star, x sub 2 star, x sub n star. These all become these sample points in the subintervals, so that if you have x sub I star, it's in the ith subinterval between x sub I minus 1 and x sub I. So let me tack that onto my drawing a little bit. So A is always x sub 0, B is always x sub n. We know that from our last discussion. The next one over would be x sub 1, here's x sub 2, x sub 3. Eventually, somewhere in here, we come across the endpoints of the subinterval called x sub I and x sub I minus 1. What this definition is saying is that anytime you've got, let's say you want x sub 1 star, it's guaranteed to be located between x sub 1 and x sub 0. So the one that's located here in between these is called x sub I star. It represents the general x value that you're going to use to find the height of your rectangle, and it lies between x sub I and x sub I minus 1. So then the definite integral of f from A to B is, now this is new notation. The right side should look very familiar. This sum from I equals 1 to n on f of x sub I star delta x, that is the Riemann sum. Without the limit, that is an estimation of area under the curve if you're looking at a graph. Without the limit, that is an estimation of area under a curve if you happen to be looking at a graph. We'll also talk about other applications for it. With the limit in front, the right-hand side now would represent the exact area under a curve if you're discussing a graph. Okay? So that's a lot of writing to do. So what we do is we shorthand that right-hand side, and instead what we write is this new notation. And this new notation is read as, it's spoken as, the definite integral of f from A to B is. And this is what the new notation looks like. Now this is of course provided that your limit actually exists and gives the same value for all possible choices of sample points. If it does exist, we say that f is integrable on A to B. For the moment, we're just going to assume all of that's true. We will, of course, discuss cases where it's not as we move forward. But for now, let's just take a look at the definition and the notation. So this is just a rewriting of what we just had on the previous slide. The limit and the summation are replaced with your integral symbol. So this little, it almost looks like a giant S, but kind of stretched out like that. That takes the place of the limit and the summation. Okay? Then we've got the dx taking the place of the delta x. Okay? If you remember when we talked about differentials, dx and delta x are not exactly the same thing. Delta x is the change in x of the function, whereas dx is the change in x of the derivative. However, we talked about the fact that those are actually equal to one another in these cases. So we are replacing delta x with dx instead. And then instead of saying f of x sub I star, we're replacing it with f of x to indicate that this holds for all legitimate values of x. If we're discussing graphs, the definite integral represents the area under the curve between A and B. As I did mention, though, this has many other applications, which is why we're taking the time to discuss it. So that's a lot. There's a lot of notation and a lot of definitions flying around, but the basic takeaway from this, here is your limit definition of a definite integral. Okay, this is the same thing we had on the previous slide. So delta x is found by taking b minus a divided by n, and x sub I star is found by taking a, the left side of your interval, plus I times delta x times those widths. So we will be integrating functions using this limit definition of an integral. It's going to take us just a little bit more conversation before we do it, but we're heading there in just a little bit. Here's some important notes before we do that, though. When you're using Riemann sums, which estimate the area under a curve, or a definite integral, which provides exact area under a curve, keep in mind what we mean when we say under the curve. We do not actually mean under the curve. We mean between the curve and the x-axis. It's a little bit of a misnomer. Up until now, I've only discussed functions where the function has been above the x-axis on the interval from a to b. That has been by design. It keeps the conversation simpler. The question we need to kind of take a look at now is what happens when it falls below. So the area, whether you're talking about an estimation or an exact, so this is with or without a limit, is the sum of the areas that lie above the x-axis with the negatives of the areas that lie below the x-axis. So if we were looking at this graph, it would be the area of the blue, you can either think of it as plus the negatives of the area in yellow, but adding a negative is the same thing as subtraction, so you would subtract it. If it helps, think of it as the blue areas would have heights that are positive because their function values are positive, whereas the rectangles that you would have in the yellow area would have negative heights because their function values are negative. It's not technically the height that's negative, it's the position, but it would result in a negative area. So the interesting thing is that as a result of this, when you calculate the area from, let's say, this A to this B, what you're getting is a net area. You're getting the positive blue area minus the yellow negative area. In other words, in theory, you can absolutely have negative area under a curve if there's more area below the x-axis than there is above, which is what this should say. That should say above. So if I were to draw you an example, if I have a function and I'm looking for the area, let's say from A to B, and my function actually looks like this, where this is the only area above the x-axis, and this is all area below the x-axis. If I don't come up with a negative answer for this particular integral or this particular area under the curve, something's gone wrong. It's supposed to be negative. The other thing we want to have just a quick recall on, we will be using a lot of summation notation as well as some of the properties of summations that you may or may not have been exposed to since your pre-calculus class. So just a quick review. We've got that the sum from I equals 1 to n on I. So I is, of course, your index. So this is literally adding like 1 plus 2 plus 3 plus 4 all the way up until n. One of the ways you can simplify that is by taking n, which is your last number, times n plus 1, which is your last number increased by 1, and dividing by 2. That's one of the properties from summations. Similarly, if you are summing from 1 to n I squared, it can be simplified to n times n plus 1 times 2n plus 1 divided by 6. And the sum from I equals 1 to n on I cubed can be simplified to n times n plus 1 divided by 2, the entire thing squared. We will be making use of these three properties over the next few examples, along with the sum from I equals 1 to n on a constant. So again, notice I is your index on this. C is a constant. There is no I in your sequence that's appearing here. That can be simplified to n times c. And then we've got the sum from I equals 1 to n on c times the sequence a sub I. C again being a constant. The constant can be pulled out front and leaving the sequence in there. This one essentially says you can split summations across addition and subtraction. So the sum on a sub I plus b sub I, you can individually sum a sub I and then add or subtract the sum on b sub I individually. Please keep in mind that that is not true in most cases for multiplication. If you have the sum on a sub I times b sub I, you may not assume you can split that to the sum on a sub I times the sum on b sub I. It's also true that you cannot split them across division. Also not true. I'm going to post this particular video separately. I'm just not going to run through it in this video, which runs you through some of the properties, gives you a little bit more practice. There is a calculator tutorial at the end, which is actually not useful for us. The calculator tutorial is excellent if you're looking to do things like end your sequence at 5. Of course, we are in calc though, so this is going to end at end. So the calculator tutorial isn't helpful, but the walk through the properties is. So I will post that separately. Feel free to watch this video if you feel like you'd like a little more review or a little more practice in those properties than what we are about to do in our examples. Okay, so let's go back and look at a Riemann sum. Go back to the estimation of area using rectangles. So we're going to evaluate the Riemann sum for f of x equals x squared, taking the sample points to be right endpoints and a equals 0, b equals 1, and n equals 5. Notice this is not yet a definite integral because I gave you a specific number of rectangles, in this case specifically 5. So this is not an integral yet. So we want to calculate our width, delta x. It's b minus a divided by n. B, the right endpoint, is 1. A, the left endpoint, is 0, and we are using 5 rectangles. So the width of each subinterval is 1/5. We also need to calculate our x's. So x sub 1, it's a plus I delta x, right? That's how you find x sub I in general. So x sub 1 is going to be a is 0. I, in this case, notice that's the index, is 1, and then delta x we just said is 1/5. So in other words, that simplifies down to 1/5. If we want to find x sub 2, again, it's 0 for a. This time I is equal to 2 times 1/5. So that simplifies to 2/5. For x sub 3, we're going to get 0 plus I is now 3 times 1/5 for 3/5. So x sub 4, I think you're going to be able to hop onto the pattern at this point. We've got 4 times 1/5, which is 4/5. And then x sub 5 will be 5/5, also known as 1. So that is how you can do this if you're wanting to generate it through the formula. Your other option is to simply say, hey, the left endpoint is 0, the right endpoint is 1, break it up into 5 equal pieces, pretend that's equal, each one having a width of 1/5. So over from 0, if you move over by 1/5, you get to 1/5. Move over one more, you get to 2/5, again and again. Just make sure that when you end on your last one, you actually end up at B, or something has gone wrong. So if we're looking to find r sub 5, let me do this using 2 different notations. So r sub 5 should be delta x, your width, times, it should be, since this is right endpoint rectangles, we're going to go f of x sub 1 for my first height. If this were left endpoint rectangles, my first height would be determined by f of x sub 0. Okay. Plus f of x sub 2, f of x sub 3, f of x sub 4, and f of x sub 5 is where I end. Now the other way to write this is to say that that is the sum from I equals 1 to 5 on f of x sub I times delta x. Okay. So 2 different, this is what we call the expanded form, and this is what we call the summation notation. Either one's great. So when I go ahead and put in my values for this particular question, the width is 1/5, the heights, x sub 1 we just talked about, it's 1/5. So the height is the function evaluated at 1/5. My function in this case is f of x equals x squared. So when I evaluate x squared at 1/5, it's going to be 1/5 squared. When I find my second height, I'll be plugging x sub 2 into my function. X sub 2 is 2/5, so the function evaluated at x sub 2 is 2/5 squared. Similarly, the next one is 3/5 squared. Then we get 4/5 squared, and finally we'll get 5/5 squared. Now you can absolutely plug this into a calculator and come out with an answer, but there's a couple of cool techniques that it helps to see as early as possible. We will be using these techniques later, so let me just show you another way you could simplify this. What we want to notice is that each one of these fractions has a denominator of 5, with the understanding that that 5 is going to be squared because of this particular function. So technically, each one of those has a 25 in the denominator. So you could, since it's present in every term, factor that 1/25 out. What you would then be left with is all the numerators. 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. And again, as I mentioned, you don't have to do this to get to the answer. It's just an interesting technique that we'll see a bit as we move forward. So we know that 1/5 times 1/25 is 1/125. And when you add up 1 squared, 2 squared, 3 squared, etc., you're going to get 55. So 55/125 reduces down to 11/25. So this is the Riemann sum for f of x equals x squared using 5 right endpoint rectangles going from a left endpoint of 0 to a right endpoint of 1. If we were looking at a graph, this would be the estimate of the area under the curve. So this is what we already knew how to do. So let's now move into the new type of question we're going to be looking at that's similar to this one. So I'm going to be asking you to evaluate the integral from 0 to 1 on x squared dx, okay, using the limit definition. So notice something. My function is still x squared, right? Our generalized notation is the integral from a to b on f of x dx. My f of x is still x squared, just like it was in the last example. My a, my left endpoint, is still 0, just like it was in the last example. And my b is still 1, just like it was in the last example. The difference between the previous question and this one is that in the previous question, I asked you to estimate using 5 right endpoint rectangles. In this one, I'm asking you to find the exact area under this curve. So this is the new stuff. We approach it in a similar way. We still start by looking at delta x. It's still b minus a divided by n. It's the length of the interval divided by the number of rectangles we're using. In our particular case, b is still 1, a is still 0. The difference is we don't know how many rectangles we're using. We're using n rectangles, a non-specified amount. So we need to leave that as n. So the length of my interval, the length of each subinterval is 1 divided by n. The way we are going to find each one of these x sub I stars, here comes that formula, a plus I delta x. Here we have to use the formula, okay? A is still 0. I, this is going to represent all of them, so we're going to leave that as I, and then times delta x, which is 1/n. So this cleans up and simplifies to I divided by n. So those are the two calculations I make to start, and then we say, okay, the integral from 0 to 1 on x squared dx is found by taking the limit as n approaches infinity. Okay, and I'm going to use the generalized limit. Let me put it up here. So it's the sum from I equals 1 to n on f of x sub I star delta x. Okay, so we'll have the sum from I equals 1 to n, f of, we just calculated x sub I star for our particular question. For us, that's I over n. We then need to multiply times delta x, so times 1/n. Okay. The last thing I'm going to do is I'm actually going to plug that I over n into the function itself. So we have the limit as n approaches infinity, I equals 1 to n. The function is x squared. So we're going to have I over n, which is our input, and then we're going to input that into the function, so it's going to get squared. Okay, so this is the setup. From here, what we now need to do is actually compute this limit, which definitely looks different than any limit that we have computed so far for a few reasons. One, it has summation notation in it. Right? We have not had to deal with that. So one of our first goals is to get rid of that summation notation. So here's where all those properties of summations come into play. What I want to do is take a look at the index. In this case, the index is I. What that means is I acts as the variable for this particular summation. That means anything that isn't I isn't a variable. It acts as a constant. And remember, what we can do with constants for summations is we can pull them out front. I'm going to start by pulling 1 over n out front of the summation notation. Notice I am not pulling it out front of the limit, because according to the limit, n has to approach infinity. So it doesn't act as a constant in front of the limit. So then I'm going to say the sum from I equals 1 to n. So I'm also going to split up the I over n squared and rewrite it as I squared divided by n squared. Right? That's just properties of exponents. But now notice I have that n squared in the denominator, which just like the 1 over n can come out as a constant. Okay? So the reason this is helpful, if you go back to those properties that I had and I said that we would be using, here's where they come into play. Recall that the sum from I equals 1 to n on I squared can be simplified. It becomes n times n plus 1 times 2n plus 1 divided by 6. And here's why this is so helpful. Notice the left side of that property has summation notation. The right side does not. And that is how we eliminate the summation notation from these limits. So we'll have the limit as n approaches infinity. We've got 1 over n cubed sitting out front. And we're going to replace the sum on I squared with n times n plus 1 times 2n plus 1 all over 6. Notice I now have a limit as n approaches infinity with absolutely no summation notation in it. So that is fantastic. Because we've already asked you to calculate limits as your variable goes to infinity. We know how to do that. I'm going to use the technique that we used in previous sections. I'm going to go ahead and simplify that numerator by distributing. I'm going to take the n times the n plus 1 times the 2n plus 1. When you do that, you're going to get 2n cubed plus 3n squared plus n. And then I'm just going to take that 6 times the n cubed. From here, we just need to calculate this limit. You have two options that we have already discussed in this course. One is to divide the numerator and the denominator by the highest powered n you see in the denominator. That's an option. You can also use L'Hopital a couple of times. That would work as well. Also, in this case, you could divide the 6n cubed into each term in the numerator. There are multiple correct ways to approach it. When you do so, I'll go ahead and do the division by n cubed. 2 plus 3 over n plus 1 over n squared. You've got 6 in the denominator. And now as we take that limit as n goes to infinity, any fraction that has a constant in the numerator and a variable in the denominator goes to 0, which means this is leaving me with 2 over 6, which means I actually get an exact value of 1/3. That is the exact value of this definite integral. So let's do a quick recap because this one's, believe it or not, relatively straightforward. And some of these, the algebra gets a little bit nastier. So let's just kind of recap what we did. First, We found the calculations for delta x and x sub I star. Next, we created a limit based on the limit definition of an integral with our particular delta x and our particular x sub I star. And then we evaluated the function at x sub I star. We then needed to compute the limit process. That involves eliminating the summation notation by moving to the front of the summation anything that does not contain an I, and then replacing what is remaining with one of the properties that we mentioned in the previous slide. We then calculate the limit using our normal limit processes. Again, it can be division by highest powered ends. In denominator, it can be L'Hopital. You have a couple of different options for how you actually compute this limit. Okay. Let's take a look at another example. In this example, we're going to evaluate the integral from 0 to 3 of x cubed minus 6x dx. So we're going to use our limit definition of an integral, which says, again, the limit as n approaches infinity on the sum from I equals 1 to n of f of x sub I star delta x is equal to the integral from a to b on f of x dx. So our delta x is going to be b minus a divided by n. For this particular question, b is the right endpoint, that's 3. A is the left endpoint, that's 0. The number of rectangles stays undefined at n, and where n represents a finite number. So that's 3 over n. And then our x sub I star is our next calculation. So that's a plus I delta x. So our a is 0. And then I times delta x, which is 3 over n. So x sub I star ends up being 3I over n. Okay, so our integral from 0 to 3 on x cubed minus 6x dx becomes the limit as n approaches infinity of the sum from I equals 1 to n. We're going to have our function evaluated at 3I over n, because that's our x sub I star, and then times our delta x, which is 3 over n. I'm going to actually evaluate our function at our particular x sub I star. So we'll have the sum from I equals 1 to n. When I plug 3I over n into my function is x cubed minus 6x. So this one's going to be, instead of x cubed, I'll have 3I over n cubed minus 6 times 3I over n. And then we're multiplying that times 3 over n. So we have the limit now set up. So now our goal is to eventually evaluate the limit, but first we need to eliminate the summation notation. We do that by using properties of summations to split these apart and pull to the front of the summation anything that does not contain an I, because again, I is your index, it acts as your variable. So the first thing I'm going to do is pull that 3 over n out. Just be careful. It applies to everything that comes after. So I'll have the sum from I equals 1 to n. So we have 3I over n cubed. Remember, you need to cube the 3, cube the I, cube the n. So that's 27I cubed over n cubed. We can also, by the way, split summations across addition and subtraction. So I'm going to split this one up. The 6 and the 3 I'm going to pull out front at the moment as an 18. So we'll have the sum from I equals 1 to n on I over n. Again, keep in mind those n's also act as constants, so they can also be pulled out front of each one of their respective summations. So we'll pull out the 27 and the n cubed from the first one. We'll have the sum from I equals 1 to n on I cubed. And from the second one, we'll pull out the 18, which is already out, and then we'll also pull out the n. Sum from I equals 1 to n on I. Okay, so now we can replace the sum on I cubed and the sum on I. They both have replacements. Recall that the sum on I is going to be n times n plus 1 over 2, and that the sum on I cubed is n times n plus 1 over 2, the entire quantity squared. So those are my replacements. So this will become the limit as n approaches infinity. We'll have 3 over n times, we'll have 27 over n cubed. Instead of the sum on I cubed, I will have n times n plus 1 over 2 quantity squared. And then we'll have minus 18 over n, and in place of the sum on I, we will have n times n plus 1 over 2. Okay. The good news is all the summation notation is gone. The bad news is we got to be very careful about making sure we do the correct simplification as we clean this up so that we can take the limit. Let me just move this to the next slide, give myself a little bit more room. We'll have the limit as n approaches infinity. We'll have 3 over n. We'll have the 27 over n cubed. Remember, that's going to be, we have to square each one of those pieces. So that's n squared, n plus 1 squared, 4. And then the second one, if you take the 18 and divide it by the 2, you're going to get a 9. The n in the numerator and the n in the denominator cancel, and you're going to get 9 times n plus 1. If we clean that up a little, n approaches infinity, 3 over n. 27 over 4, unfortunately, does not simplify, but we can leave it as a constant, 27 over 4. The n squared in the numerator cancels 2 of the n's in the denominator, leaving us with 1. And then up here we'll have n plus 1 squared, which is n squared plus 2n plus 1, minus 9 times n plus 1. So I'm going to go ahead and do two things at the moment. I'm going to distribute the 3 divided by n to both of the terms that follow. And I'm going to, in the first term, distribute the 27 to the n squared plus 2n plus 1. So I will have 81n squared plus 162n plus 81, because the 3 times the 27 gives me 81, divided by 4n squared. And then if I distribute the 3 divided by n to this one, we're going to get minus, it'll be 27n plus 27 divided by n. So again, at this point, you can evaluate each one of these limits. You can split them across the subtraction. You can divide each one of them by the highest powered n you see in the denominator, or you can use L'Hopital, either one. When you do that, you're going to get 81 over 4 for the first term. The limit for the second term is 27. So when I subtract the 2 of them and simplify the fraction, it's negative 27 over 4. So that is the integral from 0 to 3 on x cubed minus 6x dx. It's negative 27 over 4. There it is. So as you can see, some of these are getting algebraically a little interesting already. And believe it or not, because these are polynomials, x cubed minus 6x is a polynomial, these actually aren't too bad. When trying to evaluate these limits for more complicated functions, though, this can get a little cumbersome. So we want to examine some properties that can maybe help us shorten some of our steps. Before we do that, let's take a look at what a question would look like if it did have a more complicated function. So we'll set up an expression for the integral from 1 to 3 on e to the x dx. We are not going to evaluate this one, okay? So basically we're just going to set up the integral using limit definition. We're not going to evaluate the limits. So just as a reminder, the integral from a to b on f of x dx is the limit as n approaches infinity of the sum from I equals 1 to n on f of x sub I star delta x. That is the limit definition of the integral. So we go through our same first steps. We need delta x, which is b minus a divided by n. In this case, our b is 3, our a is 1, and then n is the finite number of rectangles. So it's 2 divided by n is our width of our subintervals. X sub I star is found by taking a plus I times that delta x. So in this case, a is 1, and then we'll have I times the delta x, which we just determined is 2 over n. So our x sub I star is 1 plus 2I over n. Okay? So there's 2 terms to our x sub I star, which is not what we've run into in previous examples, but definitely in the realm of possibilities. So when we set up our integral from 1 to 3 on e to the x dx, we'll have the limit as n approaches infinity, the sum from I equals 1 to n. We need the function evaluated at x sub I star, which we just said was 1 plus 2I divided by n, that's an I, times delta x, which is 2 over n. So we do need to go ahead and evaluate the function at our x sub I star. So it's the limit as n approaches infinity, the sum from I equals 1 to n. So we need the function evaluated at our particular x sub I star. Our function is just e to the x. So it's e raised to the 1 plus 2I over n. And then we're going to multiply times our width, which is 2 over n. So you can choose to leave that 2 over n where it is. You could also move it out front of your summation. But if we're asking for the integral written as a limit without evaluation, one of these 2 answers is what we're looking for. You don't need a numerical value for it. So let's talk about some of these properties of definite integral that are going to help us cut this down just a little bit. One of the first properties that we find helpful is the integral from a to b on c dx equals c times b minus a, where c is any constant. Interestingly, you can actually tell that c is probably a constant because of this dx. The dx, just like function notation, tells you the variable of integration. That dx tells you x is your variable. The other things should be treated as constants. So when you're integrating a constant from a to b, one of the shortcuts to that is taking that constant, c, and multiplying it times the length of your interval, which goes from b to a. So it's b minus a. Again, I can give you a graphical justification for it. It's not an actual proof, but I can give you a graphical justification. Your function is c, right? It's a constant. When you graph a constant function, it's a horizontal line, right? Constants in graphs mean horizontal lines. So if you graph that and then you try to find the area under the curve beginning at A and ending at B, notice the shape I just drew. It's now a rectangle where the length of the rectangle, the width of the rectangle goes from here to here. The width is b minus a, and the height of your rectangle is however high that constant is. So what they're actually doing is taking a width times a height, but it's exact in the case where your function is a constant. The next property we want to discuss makes sense if you remember the fact that integrals are a combination of limits and summations. So any property that applies to both limits and summations also applies to integrals. Hence, you can split integrals across addition and subtraction because you can do that for both summations and for integrals. So in other words, technically on the left side, you're supposed to add the functions f of x and g of x, or subtract them, before you integrate. Whereas on the right side, what we're saying is that you could instead integrate the function f with respect to x, integrate the function g with respect to x, and then add or subtract the results. That can be very helpful. The other one is, again, not a surprise if you've been paying attention to the other properties, which is if you have a constant c in front of a function, and you're integrating the constant times the function, you can pull that constant out front and multiply it by the integral of the function itself. We have a few more. We can also say that the integral from a to c on f of x dx plus the integral from c to b on f of x dx is equal to the integral from a to b on f of x dx. We are, of course, assuming that this actually exists. And again, I can kind of give a graphical explanation. This isn't a proof, but it helps give you the idea. If you've got a function, and let's say you were looking for area under the curve from a to b, assuming that c is somewhere in between a and b, let's say it's here, you could add up the area between a and c, add that to the area between c and b, and that would give you the total area from a to b. Again, you have to make some assumptions. Continuous function, c is in between a and b, etc. But that is another one of the properties we will make use of. Another one says that if f of x is greater than or equal to 0 for a less than or equal to x less than or equal to b, then the integral from a to b on f of x dx is greater than or equal to 0. Great. Again, not necessarily obvious when you're reading it in mathematical language, but based on what we've talked about, it makes sense. F of x greater than or equal to 0 means your function is positive. In other words, it's above the x-axis if you're discussing graphs. So between a and b, your function is above the x-axis. Well, in that case, remember what the integral from a to b on f of x dx represents. It represents your area under the curve f of x from a to b. And in that case, if your function's above the x-axis, then the area that results must be positive. Again, if you just kind of equate it to the graphs that we've been discussing, the properties tend to make a little more sense. The next one says that f of x is greater than or equal to g of x for a less than or equal to x less than or equal to b. Then the integral from a to b on f of x dx is greater than or equal to the integral from a to b on g of x dx. Again, a picture's worth 1,000 words. If you are graphing and you've got f of x as a function is greater than or equal to g of x on the interval from a to b. So let me switch colors. Let's say g of x is here, okay? And we are saying that from a to b, f of x is always larger. Notice we don't care what's happening over here outside of a to b. We're just talking about on the interval from a to b. Then when you integrate from a to b, f of x, in other words, you find the area under its curve from a to b, because it is larger than g of x, then the resulting area under f of x should be larger than the resulting area under g of x. Again, once you've got a picture in front of you, it makes sense. The last one we're going to discuss says that the integral from b to a on f of x dx, notice that's not the order that we normally go in, is equal to the negative of the integral from a to b on f of x dx. So in other words, if you want to switch your limits of integration, you want to switch where a and b are located, you are absolutely allowed to do that as long as you put a negative in front of the integral. So let's take a look at an example that we're going to evaluate an integral. But this time we're going to see if we can cut down on that limit process a little bit by using properties of integrals. And this is a new one, interpreting the graph in terms of area. That's a little bit new for us. Let's see if we can figure out what they mean by that. So we're looking at this integral by properties of integrals. The integral from 0 to 4 on 3 minus x dx. We can split that across the subtraction. So we'd have the integral from 0 to 4 on 3 dx minus the integral from 0 to 4 on x dx. Okay? And let me make sure I start saying this early. You may not leave the dx's off of these integrals, not because we're being sticklers for notation, but because without the dx, the integral doesn't make sense. That represents the width of those rectangles if you're talking about a graph. But also when we move into techniques that help us shorten integration, that dx is very, very important to be present. So please, just the moral of the story, don't leave that out. And that's by property 2. Note you do not have to memorize which property is which. Okay? So then notice your first integral, you're integrating a constant. So by property 1, we remember that should be 3, the constant itself, times the length of the interval, which is 4 minus 0. So that's by property 1. And then for the next one, we're going to need to use that idea of interpreting the graph in terms of area. So for the moment, I'm just going to leave this as the integral from 0 to 4 on x dx. So when they say interpret in terms of area, chances are very high they're looking for you to turn this into a familiar shape and use that relationship between graphs, between area under curves and integrals. So we know that the function y equals x is our identity line. It contains points like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc. So we know that this is what the graph of the curve looks like. It's actually not a curve at all, it's a line. So if I draw it, and then we're looking for the area under that curve from 0 to 4, notice a very familiar shape begins to emerge in this particular case, right? We're going to get a triangle. So we use the fact that we know the areas of triangles are 1/2 base times height. The base goes from 0 to 4, so that is 4, and then the height goes from 0 to 4 as well, so that is also 4. So the area of this particular triangle is 8. Please keep in mind, if they had not given me that function, if they had given me something curvy, I can't use this any longer, right? Now you're talking about an estimation, and that's not the same thing. So we are using the fact that that is a straight line to our advantage to then recognize that the first term becomes 12, the second one becomes 8 from the graph, so that the integral from 0 to 4 on 3 minus x dx is 4. 12 minus 8 for 4. That is way easier than doing the limit process. So when we can take advantage of properties and areas, we want to go ahead and do that. Let's look at one more example of using properties of integrals. If it's known that the integral from 0 to 10 on f of x dx equals 6, the integral from 0 to 6 on g of x dx equals negative 1, and that the integral from 6 to 10 on g of x dx is 13. Find the integral from 0 to 10 on f of x plus 3 times g of x dx. Okay, so we're going to use properties to split that integral across addition and subtraction and pull the constant out front. Notice the inclusion of dx in both of those integrals. So then we're going to look up at our information that we've been given and notice that the integral from 0 to 10 on f of x can be replaced with 6. We still have 3 here. Now we have the integral from 0 to 10 on g of x. Well, they didn't actually give me that in one shot. What they did, however, give me is that the integral from 0 to 10 on, the integral from 0 to 6 on g of x dx is negative 1, And then from 6 to 10, that integral on g of x is 13. So since I'm looking to find information about the integral from 0 to 10, we're going to take the integral from 0 to 6, which is -1, and add it to the integral from 6 to 10, which is 13. And once you use those properties, this really just becomes an arithmetic problem to get to 42. And that's it. No limit process involved. So that is the beginning of our conversation about integrals.